Imagine an object racing silently through the darkness of space, carrying chemical secrets that existed long before our sun was even born. Now, imagine that inside this ancient traveler are the same kinds of molecules that once helped spark life on Earth. That object is known as 3I Atlas, and its chemical composition has stunned astronomers around the world. One particular discovery immediately caught scientists' attention: the enormous amount of methanol streaming out of the comet's vapor. About 8% of everything it releases is methanol. That number might not sound dramatic at first, but in the world of comet chemistry, it is extraordinary. Comets from our own solar system usually contain only about 2% methanol. 3I Atlas is producing 4 times that amount. Methanol is not just another chemical drifting through space. According to NASA astrochemist Martin Cordner, it plays a crucial role in building complex chemistry. Methanol acts as a starting point for the formation of amino acids, sugars, and the molecules that eventually become DNA and RNA. In other words, it helps create the fundamental ingredients life depends on. Alongside methanol, scientists also detected hydrogen cyanide, another molecule with enormous importance in prebiotic chemistry. NASA researchers describe hydrogen cyanide as one of the most versatile compounds involved in forming amino acids. When scientists measured the balance between methanol and hydrogen cyanide inside 3I Atlas, the ratio turned out to be one of the richest ever recorded in any comet, whether from our solar system or from interstellar space. But methanol and hydrogen cyanide are only part of the story. Scientists also detected methane, cyanide compounds, and an unexpected surge in brightness after the comet passed closest to the Sun. Instruments revealed unusually high levels of carbon dioxide compared with what we normally see in solar system comets. Methane appeared to be trapped deep inside the comet's interior. Even more puzzling, water vapor was streaming away at about 40 kilograms every second from distances where that level of activity should have been difficult to explain. These chemical clues suggested something unusual about the environment where this object originally formed. Because of these discoveries, astrophysicist Avi Loeb offered a striking description. Rather than calling 3I Atlas a dangerous interstellar visitor, he described it as a friendly interstellar gardener. Instead of threatening life, this ancient comet may be spreading the chemical seeds that allow life to begin. In this video, we will explore every molecule scientists have detected in 3I Atlas, why their concentrations are so unusual, and what they reveal about the origins of prebiotic chemistry across the galaxy. This story is not about discovering life itself. Instead, it is about something equally fascinating: a 7-billion-year-old object from another star system carrying the exact chemical toolkit that once existed on early Earth before life appeared. Those ingredients are what make this discovery so remarkable. They show that the universe may be constantly moving the building blocks of life between stars. To understand why this matters, we first need to see how scientists actually detected these molecules. The key instrument was ALMA, the Atacama Large Millimeter Submillimeter Array in Chile, a network of 66 powerful radio telescopes designed to identify complex molecules in space. And what those telescopes saw inside 3I Atlas would soon change the way we think about chemistry traveling between stars. In the next part, we'll dive into the remarkable observations that revealed exactly what this ancient comet is made of. To understand why the chemistry of 3I Atlas is so extraordinary, we first have to look at how scientists actually discovered these molecules in the first place. Detecting chemicals in a comet that originated outside our solar system is not simple. It requires some of the most advanced instruments ever built, and in this case, one observatory played a central role: ALMA, the Atacama Large Millimeter Submillimeter Array in northern Chile. ALMA is made up of 66 radio telescopes working together as a single powerful system. Its job is to detect extremely faint signals from molecules drifting through space. Each molecule emits a unique rotational signature when it interacts with radiation, and ALMA is designed to capture those signals with remarkable precision. NASA astrochemist Martin Cordner led one of the teams studying 3I Atlas using ALMA. Between August and October of 2025, his team carefully observed the comet on multiple occasions. What they found was unmistakable. Methanol and hydrogen cyanide were clearly present, and their signals showed that these molecules were not only surrounding the comet, but also coming directly from its rocky nucleus. Methanol was detected throughout the expanding cloud of gas known as the coma, the glowing atmosphere that forms when a comet heats up near a star. Even more intriguing, the amount of methanol being released increased sharply as the comet approached about 2 astronomical units from the Sun, a region where water ice typically begins to sublimate. That timing was an important clue. It suggested that the warming of the comet was triggering deeper layers of ice to release their stored chemicals. As the Sun's heat reached the surface, buried molecules that had remained frozen for billions of years were suddenly escaping into space, but ALMA was only the beginning. Several other observatories joined the investigation, and together they began assembling the most detailed chemical inventory ever recorded for an interstellar object. NASA's SphereX Observatory, the spectrophotometer for the history of the universe, also monitored 3I Atlas. It observed the comet in August and again in December of 2025. During the December observations, scientists saw something dramatic. Roughly 2 months after the comet passed closest to the Sun, it suddenly brightened. The eruption released additional molecules, including methanol, cyanide compounds, and methane. This sudden increase in activity revealed chemicals that had been locked deep inside the comet's interior. Other telescopes added even more pieces to the puzzle. The James Webb Space Telescope detected carbon dioxide, water vapor, carbon monoxide, and carbonyl sulfide. Another instrument identified methane and even traces of nickel vapor escaping from the comet. Meanwhile, NASA's Swift Observatory detected hydroxyl emissions, which are a clear signature of water breaking apart under solar radiation. These observations indicated that water was escaping from the comet at roughly 40 kilograms per second. Even ground-based observatories contributed critical data. A radio telescope in South Africa detected hydroxyl absorption lines, marking the first time an interstellar comet had been observed using this radio technique. Each telescope used different methods and wavelengths, but their results all pointed to the same conclusion. 3I Atlas contains an extraordinary mix of molecules: water, carbon dioxide, carbon monoxide, carbonyl sulfide, methanol, hydrogen cyanide, methane, nickel vapor, and hydroxyl. Together, these independent measurements formed a remarkably consistent picture. For the first time in history, scientists had constructed a detailed molecular map of a comet that originated in another star system. And among all the chemicals detected, one molecule continued to stand out above the rest. Methanol was present in unusually large amounts, far higher than anything astronomers typically see in comets from our own solar system. In the next part, we'll explore why methanol is so important to the chemistry of life and why its abundance in 3I Atlas may reveal clues about the ancient star system where this mysterious object was born. Among all the molecules discovered in 3I Atlas, methanol stands out more than any other, not because it is complex, but because of the role it plays in the earliest stages of life's chemistry. Methanol is actually a very simple molecule. Yet, in prebiotic chemistry, simplicity can be incredibly powerful. This molecule acts as a starting point for reactions that eventually lead to far more complicated compounds. Scientists know that methanol can transform into formaldehyde, and formaldehyde can combine with other molecules to create ribose, the sugar backbone that forms the structure of RNA. RNA is one of the key molecules involved in genetic information, making this pathway critically important for the chemistry that precedes life. Methanol is also linked to the formation of amino acids through a chemical process known as the Strecker synthesis. Amino acids are the building blocks of proteins, and proteins are essential for the structure and function of living cells. This means methanol does not directly create life, but it helps build the chemical environment that makes life possible. Martin Cordiner, the NASA astrochemist studying 3I Atlas, has emphasized that reaching high levels of chemical complexity is extremely difficult without methanol acting as an early ingredient. That is why the amount found in 3I Atlas is so surprising. In most comets from our solar system, methanol makes up only about 2% of the volatile material being released, but in this interstellar visitor, methanol accounts for about 8%. That is 4 times higher than the typical value scientists are used to seeing. This difference is not minor. It suggests that the environment where 3I Atlas formed was dramatically different from the one that produced the comets in our own solar system. The high methanol concentration provides a strong clue about the comet's birthplace. Methanol forms most efficiently in extremely cold regions of space known as molecular clouds. These are the dense, frigid environments where new stars and planetary systems begin to take shape. In these clouds, carbon monoxide molecules freeze onto tiny dust grains. Hydrogen atoms then attach themselves to the carbon monoxide in a step-by-step process called hydrogenation, gradually transforming it into methanol. The colder the environment, the more efficiently this reaction occurs. 3I Atlas appears to carry the chemical signature of exactly such a cold environment. Its unusually high carbon dioxide levels already hinted that it may have formed in a colder protoplanetary disk than our solar system. The methanol enrichment strengthens that conclusion. In other words, the chemistry inside this comet likely formed in a star system where temperatures were lower and organic molecules were more abundant. The second major molecule detected, hydrogen cyanide, adds another crucial piece to the puzzle. Hydrogen cyanide has a reputation as a toxic substance, but in prebiotic chemistry, it plays an essential role. When hydrogen cyanide reacts with itself and with water, it can produce adenine, one of the 4 nucleobases that make up DNA and RNA. It also participates in the same Strecker synthesis pathway that forms amino acids. NASA scientists often describe hydrogen cyanide as one of the most versatile molecules involved in the creation of life's chemical precursors. What makes 3I Atlas especially interesting is the ratio between methanol and hydrogen cyanide. The comet contains far more methanol relative to hydrogen cyanide than scientists usually observe. Avi Loeb interpreted this unusual balance as another reason to call the object a friendly interstellar gardener. Instead of being dominated by harsh chemicals, its composition favors the production of complex organic molecules. Then, in December 2025, something unexpected happened. Roughly 2 months after passing closest to the Sun, 3I Atlas suddenly erupted with activity. Instead of fading as it moved away from the Sun, it became dramatically brighter. This surprising event was caused by a delayed thermal process deep inside the comet. And what that eruption revealed would give scientists a rare look into material that had remained frozen and untouched for more than 7 billion years. The sudden brightening of 3I Atlas in December 2025 puzzled astronomers at first. Normally, Comets are most active when they are closest to the sun, because that is when solar heat causes their icy surfaces to vaporize, but in this case, the major outburst happened nearly 2 months after the comet had already passed its closest point. Instead of cooling down, the object suddenly erupted with fresh activity. Scientists eventually explained this behavior through something known as the thermal wave effect. When a comet approaches the sun, heat does not immediately reach its deep interior. Instead, the warmth slowly travels inward through the surface layers. That heat wave can take weeks or even months to penetrate deeper into the comet's structure. When it finally reaches pockets of highly volatile ices buried beneath the surface, such as methane or carbon monoxide, those materials suddenly begin to sublimate. The rapid release of gas can create a delayed eruption long after perihelion. That is exactly what happened with 3I Atlas. As the thermal wave reached deeper layers of the comet, it triggered the sudden release of trapped gases. Methanol, hydrogen cyanide, and methane burst out from regions that had remained sealed and frozen since the object first formed billions of years ago. This eruption gave scientists an extraordinary opportunity. For a brief moment, the interior chemistry of an ancient interstellar object was exposed to observation. The data collected by Spherex during this event confirmed that the comet was releasing molecules that had never been altered by sunlight or solar radiation during its long journey. These chemicals had been locked away inside the comet since its birth in another star system. Over billions of years, traveling through interstellar space, they survived exposure to cosmic rays, extreme cold, and the emptiness between stars. This discovery highlights an important scientific concept known as panspermia. Panspermia is the idea that life, or the ingredients needed for life, might travel between planets or even between star systems. However, scientists divide this idea into several different forms. The first is known as weak panspermia, sometimes called molecular panspermia. This version suggests that the building blocks of life's simple organic molecules can move through space and be delivered to young planets. A second possibility is strong panspermia, which proposes that actual living organisms might survive the journey between stars. This would require microbes or other biological material to remain alive for extremely long periods in the harsh environment of space. A third idea is directed panspermia, which suggests that an advanced civilization might intentionally spread life by sending biological material to other planetary systems. The observations of 3I Atlas strongly support the first idea, weak panspermia. They show that complex organic molecules can indeed survive interstellar travel. The methanol, hydrogen cyanide, and methane detected in the comet are not alive, but they are precisely the types of chemicals that participate in life-forming reactions. What makes this discovery remarkable is that the molecules appear to have traveled billions of years through space without being destroyed. When the comet entered our solar system and warmed up, those chemicals were still intact and capable of reacting with other materials. This demonstrates that interstellar objects can act as carriers of prebiotic chemistry. In other words, the universe may be constantly transporting the ingredients for life from one planetary system to another. 3I Atlas does not prove that life itself travels between stars, but it clearly shows that the chemical toolkit for life can make that journey. And as scientists continued studying its composition, they realized that its unusual chemistry might reveal something even deeper clues about the ancient star system where this remarkable object first formed. As scientists continued examining the chemistry of 3I Atlas, they began to realize that the unusual mix of molecules was not random. Each measurement pointed toward a very specific type of birthplace. The comet's chemistry suggests it formed in a planetary system very different from our own one, that was colder, richer in carbon, and likely much older than the Sunday. One of the most striking clues is the methanol concentration. With methanol making up roughly 8% of the comet's volatile material, it indicates an environment where cold interstellar chemistry was extremely efficient. In such conditions, carbon monoxide freezes onto dust grains and gradually transforms into methanol through hydrogenation reactions. These reactions occur most effectively in very low temperatures, which means 3I Atlas likely formed far from its parent star, in the outer regions of a cold protoplanetary disk. Other measurements reinforce this picture. The comet contains unusually high levels of carbon dioxide compared with typical solar system comets, sitting far above the usual chemical trend astronomers observe. Methane was also found buried deep inside the comet's interior, suggesting it condensed at extremely low temperatures and remained sealed away for billions of years. Even the ratio of nickel to iron detected in the vapor hints at a parent star that formed in a region with slightly different elemental composition, possibly a star older than our Sun, and formed when the galaxy contained fewer heavy elements. Altogether, these clues paint a fascinating portrait. 3I Atlas appears to be around 7 billion years old. That means it formed roughly 2.5 billion years before the Sun even existed. In a sense, this comet is a preserved chemical fossil from an earlier era of the galaxy. The molecular mixture it carries gives scientists a rare glimpse into how planetary systems formed and evolved long before our own solar system took shape. But the implications extend far beyond one ancient object. Astronomers now believe that interstellar visitors like 3I Atlas may be far more common than once thought. Based on current detection rates and models of how often these objects pass through planetary systems, researchers estimate that at least one similar interstellar object may pass within about 4.5 astronomical units of the Sun at any given time. Over the past decade alone, astronomers have identified several such visitors, including Oumuamua, Borisov, and now 3I Atlas. These discoveries suggest that our solar system is not isolated from the chemistry of the wider galaxy. Instead, it may constantly receive small deliveries of molecular material from distant star systems. Some of these objects pass harmlessly through space and leave again. Others might collide with planets or moons, depositing their chemical cargo onto planetary surfaces. This idea becomes even more interesting when we think about Earth's early history. Roughly 4.1 to 3.8 billion years ago, our planet experienced a period known as the heavy bombardment. During that time, Earth was struck frequently by comets and asteroids, delivering enormous quantities of water, organic molecules, and volatile materials. If interstellar objects like 3I Atlas were also part of that bombardment, they could have contributed additional chemistry to Earth's surface. With methanol concentrations 4 times higher than those found in typical solar system comets, such objects might have enriched the young planet's chemical environment. While scientists cannot prove that interstellar comets helped trigger life on Earth, the possibility is now grounded in real, measurable chemistry rather than speculation. However, it is important to remain clear about what these findings do and do not show. The molecules inside 3I Atlas are prebiotic. They can participate in life-forming chemistry, but they are not alive themselves. No evidence of living organisms, biological processes, or metabolism has been detected on the comet. Yet the discovery still carries enormous significance. It proves that the chemical toolkit that once preceded life on Earth exists elsewhere in the galaxy. And it proves that those molecules can travel across interstellar space for billions of years and still remain intact. In the final part, we'll explore what this means for the future of astronomy and why scientists believe discoveries like 3I Atlas could completely reshape our understanding of life in the universe. When all the evidence is brought together, the story of 3I Atlas becomes both simple and profound. This ancient interstellar comet does not carry life. There are no microbes hidden in its ice and no signs of biological activity. But what it does carry may be just as important: the raw chemical ingredients that allow life to begin. The molecules detected inside the comet form a powerful prebiotic toolkit. Methanol, hydrogen cyanide, methane, carbon dioxide, water, and other compounds are all known to participate in the chemical pathways that lead to amino acids, sugars, and nucleobases. These are the building blocks required for proteins, RNA, and DNA. On early Earth, similar molecules played a critical role in the chemical reactions that eventually produced the first living systems. What makes 3I Atlas remarkable is not just the presence of these molecules, but their survival. The comet appears to have formed roughly 7 billion years ago in another star system. After forming, it was likely ejected into interstellar space, where it drifted through the galaxy for billions of years. During that time, it endured cosmic radiation, freezing temperatures, and the near-perfect vacuum between stars. Yet despite those harsh conditions, its chemistry remained intact. When the comet finally entered our solar system, solar heat activated those ancient ices. Methanol, hydrogen cyanide, and methane began escaping into space, allowing telescopes to detect them for the first time. Multiple observatories, ALMA, SPHEREX, the James Webb Space Telescope, SWIFT, and others, confirmed these molecules independently. Each instrument used different techniques, yet their results all pointed to the same conclusion: this interstellar object carries an unusually rich supply of prebiotic chemistry. This is why astronomer Avi Loeb described 3I Atlas as a friendly interstellar gardener. The comet does not bring life itself. Instead, it spreads the seeds of chemistry that life requires. Whether those seeds ever grow depends entirely on the environment where they land. On a young planet with liquid water and the right conditions, these molecules could participate in complex reactions that slowly build toward living systems. And 3I Atlas may not be unique. With powerful new surveys coming online, especially the Vera C. Rubin Observatory and its legacy survey of space and time, astronomers expect to detect many more interstellar objects in the coming years. Some estimates suggest that thousands of these visitors could eventually be identified, each carrying its own chemical fingerprint from another star system. If that is true, then the galaxy may be constantly exchanging molecular material between planetary systems. Comets and asteroids could act as natural carriers of prebiotic ingredients, quietly spreading organic chemistry across vast distances. Instead of isolated islands, planetary systems might be connected by a slow but steady flow of molecular building blocks. 3I Atlas offers the first clear evidence that this kind of chemical transport is possible. Its composition provides a snapshot of the galaxy as it existed billions of years ago and shows that the ingredients for life can form far beyond our solar system. More importantly, those ingredients can survive the journey between stars, and that realization changes how we think about life in the universe. If the basic chemical toolkit for life is common and mobile across the galaxy, then the conditions that once helped life begin on Earth may not be rare at all. If you enjoyed this deep dive into one of the most fascinating interstellar discoveries ever made, make sure to like the video, subscribe to the channel, and share it with someone who loves space as much as you do. And in the comments, tell us which molecule from 3I Atlas surprised you the most, because the more we explore the cosmos, the more it seems the seeds of life may be traveling everywhere.